Homework 3, problem 12, find the location and sign of the image charges for the following situation, and then show that the magnitude of the electric field falls off as 1 over r to the 4th as you go very far away from the system. Start out the image charges. I have 2 planes here, so I can just guess to start out that I might put an image charge of minus q below each plane. So a distance a and a below the 2 planes, so on the left-hand side of the vertical plane and below the horizontal plane. But now if I think about it, although the potential from the positive charge and the negative charge exactly cancel on this plane, the potential from this negative charge no longer does. In order to cancel it out, I can introduce an image charge to the image charge, which will be a plus q here. And now the potential from this minus q and plus q will cancel out on this plane as well. It turns out the same thing happens here. The potential between this plus q and this minus q cancel out on this horizontal plane, but the potential for this wouldn't unless I have this guy. And so these are my image charges. If I write them out each individually, I'm going to have an image charge of minus q. Okay, so this will be my charge, and my position is going to be, the first one is minus a in the j hat direction, and plus a in the k hat direction, right? Then I'm going to have another image charge of minus q that's in plus a in the j hat and minus a in the k hat. I'm an image charge of plus q at minus a in the j hat and minus a in the k hat. And so there is the answer to the first. Find the location and sign of the image charges. The second problem is a bit more difficult, and so let me go ahead and show you what I was thinking there. If I were to draw this plane, and then I were to draw the charge in its images, okay, and I'm going to draw them very small such that we're very far away. Okay. Charge in its images. If I then look at a field point that's very, very far away, okay, this field point r, okay, I define that vector theta there for a moment. When I think about the electric field due to each one of these charges, for the 2 plus charges, the electric field is going to be in the same direction and along that direction. Pretty much. The difference between the alignment here and the direction from the charges will be very small if I'm far away. And then for the 2 minus charges, I would have the field point backwards along that. And so as a first approximation, I can say that the electric field is going to be the magnitude of the electric field for each one of these. And so for the 2 positive charges, I'm going to have q over 4 pi epsilon naught. I'm going to have that out front, and I'm going to do the 2 positive charges first. The positive charge, I'm going to set, for the moment, I'm going to set, this is, remember, this is the y, and this is the z. I'm going to pretend I'm in the x-axis plane. So this is 1 over y minus a quantity squared plus z minus a quantity squared. So that's the first charge. The other positive charge is at minus a, so that's going to be y plus a quantity squared and z plus a quantity squared. Below, I'm going to get, for the 2 minus charges, so I put a minus out front, y is in the minus sign, so y plus a quantity squared plus z minus a quantity squared. And I'm going to come over here, oh, it's a minus as well, y minus a quantity squared plus z plus a quantity squared. And so this is an approximation, that's in the r hat direction. This is a first approximation to what the electric field will look like for that situation. In order to examine how the electric field is going to fall off, I have to replace my x and my y with r, right? And so keeping those there. I'm going to say that my y is going to be equal, looking at my diagram, the y is the cosine part, so this is r cosine phi, and my z is equal to r sine phi. And so when I have this expression, let's just simplify it. 1 over y plus or minus a quantity squared plus z plus or minus a quantity squared, which I'm going to rewrite this here in different colors. Okay, so rewrite this. This is 1 over y plus or minus a quantity squared. Wrote that in blue, and then in red we'll do the z, plus z plus or minus a quantity squared. I'm now going to make the replacements for y and z, and so I'm also going to write this expression as the inverse. So coming here, this is now going to be r cosine theta plus or minus a quantity squared plus, and I'm going to get r sine theta plus or minus a quantity squared, and -1. Okay, now we simply expand these. We're going to get an r squared cosine squared and an r squared sine squared, which is going to add to the to r squared. So we're going to get r squared, then plus, now we'll do the cross terms. And so here's where I wanted to do different colors. The cross term here is going to be plus or minus 2 ra cosine theta, and then I get a different plus or minus 2 ra sine theta, and then we get always going to get a plus 2a squared. So this whole thing to the -1th power. At this point, we can factor out this. At this point, we want to make this statement. We know that the radius is much, much bigger than a. And so we're going to factor that out. And so this thing is equal to 1 over r squared. And then it's going to be 1. And now we're going to be a little interesting here. Plus 2r over a, and then plus or minus cosine phi plus or minus sine phi. Plus 2 a over r, 2a squared over r squared. This to the entire -1th power. So why did I do all of that complex stuff? Why did I do all that crazy stuff? It's because now I'm going to take this expression and replace that with the electric field. So the electric field is going to be q over 4 pi epsilon naught r squared. We're factoring out this r squared. And then I'm going to come here and I'm going to write down what I have. I'm going to have 1, let's see, I have minus minus, so I'm going to get minus both. So minus 2a over r cos theta plus sine theta plus 2a squared over r squared minus 1 plus 1 minus, and so that's this one. This will be plus, not minus, plus 2a over r cosine theta plus sine theta plus 2a squared over r squared. And then minus 1, and now we have to be a little bit careful. For this one, I have plus on the first one and minus on the second. So I'm going to say plus 2a over r cosine theta minus sine theta plus 2a squared over r squared, the negative 1th power, minus 1 minus 2a over r cos theta minus sine theta plus 2a squared over r squared to the minus 1 power. Okay, so we have all of that lovely stuff there. Continuing on with the problem, we now use the final trick at our disposal, which we're going to use the binomial expansion, which is 1 plus a to the nth power. For a small goes as 1 plus na plus n minus 1 over 2 a squared plus dot dot dot. For us, this is going to be 1 plus x to the minus 1 power is going to be 1 minus x plus x squared minus dot dot dot. And 1 minus x to the minus 1 power is 1 plus x squared plus dot dot dot. Well, why do we care about that? Because now we can expand, because a over r is tiny. And so we can expand each one of these things. From the first two terms, we immediately see that the ones, they have plus 1, minus 1, minus 1. Those are going to cancel. Second, we see that since these are opposite signs, we're going to get a plus here and a minus here, and these are going to cancel to first order. And so the lowest order term that we're going to get is going to come from the squared term. So we'll get squared terms twice. We'll get it from the first expansion of this and the second expansion of that term. But in any case, I can now make the statement that this whole thing scales as a squared over r squared. Okay? And so using that argument, which came from here and came from cancelizations, I have that the electric field is proportional now to a squared over r to the 4th, r hat, which is what I wanted to show. Okay, so I'm not sure why I asked that. That was a difficult question. Hopefully everyone did all right on that. Okay, thank you.